Yeah, thank you very much, ladies and gentlemen. Thanks for the invitation here to be here tonight to tell you what I'm doing every day. I thank especially Ravi for the invitation, for inviting me and for hosting me during this week. As mentioned, the title of my presentation here tonight is Vehicle Track System Dynamics and Long-Term Behavior. So what I will be covering during the next 50-odd minutes, after a brief introduction, we'll look into the vehicle track system stress state, which will be followed by looking at some of the important rolling stock and track design parameters, taking that to a possible shrinking, or taking that to the forces at the wheel rail interface and a consequential shrinking of the factor of safety. Then I will focus on the issues of long-term behavior with respect to the track and system itself, and then also long-term behavior with respect to the wheel-related damage. Now, nothing of this would be known to us if we would not monitor these parameters, and I'll talk on that a bit. Then, again, you can't leave it as monitored results. You would use preventive and corrective measures. That will bring us back to the stress state before we end the presentation with some remarks on the issuing and achieving of operational efficiency. So as we all know, we get increased operational demands on our railway system, be it axle load, be it train speed, be it train length, be it the window of opportunity for maintenance on both the rolling stock and on the track. So increased operational demands are what we're seeing on a daily basis. Now, this usually comes together with financial constraints. Do this and that, but let it not cost too much. That kind of approach. But what I'm saying here tonight is don't save yourself into trouble. Be advised, be knowledgeable about the cause and effect in your system so that you do spend the money on the right things to achieve the best result. What we have to realize in trying to optimize the system of operational demands, the financial constraints, and what we have to deliver to our shareholders is that the maintenance we have to do on the track is, amongst others, load dependent. So if the load increases, we could expect to do more track maintenance. The problem is that usually this is not a linear relationship, but rather an exponential relationship most of the time. And we have to be quite aware of that, because if we compare a system which has got a linear degradation to one with an exponential degradation, we have to react differently. We have to find a cost-effective balance between the operational demands and maintenance. To be able to do this in an effective way, in an engineering kind of way, we need to understand the short-term and the long-term behavior of our vehicle track system. Short-term is really defined by catastrophic failures, high dynamic forces. If you get a flat spot on a wheel, it could fail the rail immediately, amongst others. Or at the long term, which is really the fatigue-related and the deterioration, the track deterioration-related parameters. So we have to understand these two concepts to be able to analyze the interaction between the vehicle and the track. So we have to look at poor vehicle performance, we have to look at the track condition, we have to look at the wheel rail contact conditions, because all of these together, in some way or the other, can easily increase the stress state in the system. And if there is stress in the system, there is an argument between the track and the rolling stock, and the loser is both of them. So we need to be aware of these interrelationships. We have to work smarter within our economic constraints. And again, through that, we need knowledge, we need skills to do this. And I think that is where the University of Monash, for example, is putting a lot of emphasis that we can gain this knowledge for this environment here. So let's turn our attention to the vehicle track system stress state. What we've got here on the x-axis is an increasing force or increasing strength parameter. Now at some point along that line, we will design our track structure. It will have a certain strength. It will be designed, for example, for a certain axle load. On the other end of the spectrum, we have got rolling stock, which has got its own load, which it has to be carried by the track. There are forces that will be interacting between the rolling stock and the track. The good news is if these things are far apart, then we can easily manage the lifespan of the track and of the rolling stock. So we've got a very nice factor of safety. But unfortunately, the world is not as ideal as we see it here, and we have to move on. We have to ask, why do we have varying forces? Why do we have varying strength factors? And what are we doing with them? Do we understand the relationship between the forces going into our system and the design parameters of the system? So we need to know the most important design parameters. Looking at the rolling stock design parameters, the car body structure is an important element which must not be forgotten in the background, because it will ultimately see what is happening between the wheel and the rail. On the bogie side, which is our important shock absorber, our suspension element, we need to look at the structure of the bogie. Can the bogie structure itself survive all the forces that will go through its system? The suspension, is the suspension tuned for the track structure which it goes over? Is it able to last long enough, or will it have a fatigue failure? Is the material used for the coil springs of a suspension system, is that well designed, and the heat treatment, and is all of that okay? Are we overloading our suspension? Then on axle spacing, that has an influence how the vehicle interacts with the track. We look at the wheel diameter. A bigger wheel diameter, bigger contact area, maybe less stress, but there's other very important aspects when we look at wheel diameter. The wheel profile, very, very important. For those that don't work with wheel profiles or rail profiles every day, here it is 0.1, 0.2 of a millimeter making the difference between a good wheel profile and a bad wheel profile. Very sensitive and not known to many people out there. They see this big train moving past and not really looking at the detail which has gone into that. Even the back-to-back distance between wheels needs to be chosen for a particular reason. So these are some of the design parameters. And on the wheel material, the list is a bit longer because the material of the wheel and the design of the wheel is really the essence of why we have a railway. We have to have material which a good resistance to wear, and that needs hardness. Resistance to plastic deformation, here we need the yield strength. Resistance to rolling contour fatigue, here we need the shear strength. Toughness against crack growth. So all of these demands, not one after the other, simultaneously. The brake system is also an important element if we look at the vehicle track system, because it influences the behavior of the wheel profile, it influences the rolling of the wheel. It could result in skid marks, overheating of wheels, things like that. And not to forget the locomotive drivetrains. Quite often what happens between the wheel and the rail, what happens in the vehicle track system already starts in the drivetrain of the locomotive, the control of the traction motors, the supply of the power to the traction motor. Very complex systems with which, if they are not balanced, can cause trouble in our vehicle track system. Those were the rolling stock design parameters, the track design parameters. Generally, we've got the track layout, we've got the gradients, the curvature, the super elevation or cant, the track gauge, meaning not necessarily the minimal gauge widening which we get on our particular track, but rather the variation between standard gauge and 3'6" and the Russian gauge and then the Victoria gauge, and everyone has got its own unique gauges, so that must be taken into consideration in relationship to those layout of the track parameters. Track geometry, very, very important aspect to understand where it's coming from, what you can do to maintain it, and how you should specify that. The superstructure, the rail, not only the rail profile, but the size, the inclination, the way it is sitting on your sleepers, the profile of the rail, rail fasteners, rail pads, all of this makes the total system, the sleeper, the type, as well as the spacing of sleepers. You can have a different spacing to have a different outcome in your design parameters. The substructure of the track, the ballast, the sub-ballast layers, and all the nice tools which are put there to keep the substructure intact under enormous force conditions, weather conditions, drainage conditions, all of that needs to be considered. Similar to the wheel, the rail material, we need again the resistance to wear, resistance to plastic deformation, resistance to rolling contact fatigue, and the toughness against crack growth. So having a system of rolling stock design, choices being made, the track system is all there. What will now happen if the first locomotive hauls the first train out of the station? There will be forces between the wheel and the rail. There will be forces at this interface. And I would like to list a few of these forces. I'll start with the lateral forces, and I'll look at some contributing factors, factors that will contribute that these lateral forces can be smaller or can be larger. The flanging of the wheel will generate rail forces, lateral forces. The creep forces will also act along the lateral plane of the wheel-rail interface. We look at curve radius. Obviously, if we go through a particular curve at different speeds, there will be different lateral forces. We look at the coupler angle. If we have got in-train forces, the coupler angle will pull or push the rolling stock in or outside of the curve, generating a differential lateral forces. Lubrication will influence the lateral forces you have got between your wheel and your rail. The speed of the vehicle, the buff and draft forces which I've mentioned, the worn suspension component, be it worn wedges or side frame pockets, whatever it is for your particular bogie. Wheel diameter mismatch. If you've got a small and a big wheel on one axle, if you've got a big differential between the wheel set diameters from between bogies, they all need to be looked after and can influence the dynamic behavior and thus the lateral forces. The bogie turning resistance, if the bogie turns against a high coefficient of friction, it will first have to generate higher lateral forces for it to steer around the track. The track misalignment itself, if the track is not well aligned, it will throw the vehicle from left to right, and we will see higher lateral forces. Traction and braking, the influence of traction and braking on the netto remaining friction force available to steer the vehicle. So these are some of the natural forces generated. And similar, we've got some vertical forces. The vehicle weight is an obvious case. The curve superelevation, it depends on the speed we go. The superelevation there is, we will have wheel unloading or wheel loading. The speed is there. The track misalignment, again, will change the vertical forces constantly. Torsional stiffness of the vehicle body, if you've got a tanker, then it has got a high torsional stiffness. Its suspension will have to react differently to maybe a flatbed wagon, which has got a low torsional stiffness. Skew and shifted loads, especially for us that, like in South Africa, we operate on narrow gauge. There it makes a huge difference if you have got a shifted load. Torsional stiffness, okay, I've got that one. The worn friction wedges, again, will influence the vertical load. Broken or missing springs, the torsional stiffness of the bogie itself. Rigid frame bogies will react different to the three-piece bogie, for example. And then whether you've got a side bearer clearance or not a side bearer clearance, which would influence the curving resistance, which can also again influence vertical forces. What we must not forget, it is eventually the ratio of vertical and lateral forces which dictate to a large extent the probability for a flange climb or wheel lift derailment. So not only will it deteriorate the system, not only will it challenge us to operate smarter, we also have a looming derailment situation. So back to the vehicle track system stress state. So now we haven't got just a single line anymore. We now have got a bit of a distribution, let's say on that side for the well-maintained track, but the track is not perfect. There's always a bit of a bump here and a bit of a deviation there. But let's argue this is now well-maintained track and it's got quite a narrow normal distribution. On the rolling stock side, the similar things happen. We've got a bit of deviations in the suspension stiffness, and we've got a bit of a few changes on the wheel profile and so on. So immediately we get a bit of a distribution of the forces around the originally designed mean value. So what happens now is the factor of safety is going to be reduced, and this is really the factor of safety we've got left. Now, should it be that our track structure is a bit older, a bit less maintained, we will have a wider normal distribution. So the statistical distribution increases. But the average of the design has not changed yet. It is just the way it works in real life. But the boss comes through the door and says, increase your axle load. That is what is happening. And due to that shift in the loads and the forces which will interact between the vehicle and the track, we now have got the problem and the challenge where the worst wagon meets the weakest track. And this is our challenge in the vehicle track interaction wheel rail interface world, to get rid of that red triangle there, or to manage it, to get it as low as possible. So to manage this conflict between the structural strength of the track and the loads coming from the rolling stock, and to do an informed decision, we need to not only look at the impact of a flat wheel in terms of a once-off occurrence, we need to look at the long-term vehicle track system behavior. And I will be looking at its behavior by example for the rolling stock, for the wheels, the rails, and for the track. So we look at the long-term behavior. The rolling stock long-term behavior, this is one typical example, structural fatigue. This locomotive has been running for a while, and we see there's a fatigue crack between the axle box and the motor case. So we need to know, why did this happen? Was the force too high? Was the design too weak? Was the material that is used, the manufacturing of these components, was that flawed? So we need to sort that out and get it out of the system. Suspension deterioration. Has the coil spring, was it broken due to material defect? Was it overloaded? Was it in the system for too long already and it has failed on us? The bearing, similar to the suspension deterioration. Has something going wrong? Have we been overloading it in a static way? Do we know the dynamic increment which works onto this component? Have we estimated it to be 30%, but it was maybe 40%? So we need to study that and do the necessary corrective action. Also component wear. This is an extreme case, and it's quite an interesting case. You can see that the center bowl of the bolster is totally worn away, and it is basically possible to cause even a derailment. Now, we can say maybe it's the material used, but in this particular case, it's quite interesting. We have got for our normal three-piece bogies a certain speed restriction. We say it can go 80 kilometers an hour on a daily basis in the empty and in the loaded condition. But here we have got a bogie which shows problems of hunting. because this kind of wear is associated with wagon or vehicle hunting. What we found out is that certain vehicles are loaded with steel coils, with the steel coils on the further ends of this particular vehicle, causing this dark bone inertial effect and reducing the hunting speed from 80 to 65. So again, does not help just to fix a problem all the time. Go and investigate behind the scenes, and then you can really use your engineering knowledge to sort out the long-term behavior of your rolling stock. Similar for the wheels and the rails, but I will come back to this point a bit later. So we rather look now at the track long-term behavior. Also, I've got 4 examples. The substructure deterioration. So what we're seeing here is the track settles. We do a tamping, a restoring of the ballast action. We come back a few load cycles later. We're back to where we were a couple of weeks ago or months ago. And we do this in a repeated way as our load cycles increase over this particular track section. But through this action, we're causing a lot of ballast damage. Through the tamping action, the ballast stones, the edges are breaking off. It changes the property of the ballast in terms of stiffness and in terms of the energy which it can absorb before it hits into the substructure. So again, we need to now understand this cycle so that we can influence it very well. And I will, almost like the second last slide, come back to the financial impact of doing this right or doing this wrong. Component failures on track components failure. Here we see the rail fastener has been fatigued off, should have maybe been replaced earlier. So again, it is a long-term behavior which you need to know of all your track components. Track geometry is a very obvious one which deteriorates in front of our eyes, and there we also need to be very smart to control that, because as you let it go, it goes quicker and quicker, and your chance to catch it up becomes more remote. Then a specific kind of behavior of long-term track behavior is sleeper skewing, which happens generally in some of the curves where there's high traction available. And if the loads of the wagons behind the locomotives are light loads, the track rail basically separates itself from the sleeper, which separate themselves from the ballast, and they start moving. When the train is passed, they find a new place to sit on, and in that process, the sleeper is actually misaligning itself relative to the rails, and that in itself could change track gauge and cause further deterioration to the ballast stones. So now we come to the wheel-rail interaction related damage, long-term behavior, and I will be looking at quite a number of categories and examples here. The wear-related phenomena, the stress-related phenomena, and dynamic-induced phenomena. So let's start with the wear-related damage. One of the very obvious ones is thin wheel flanges, as we can see over here. Now, that is the damage. The consequence could be a facing point derailment. If we look at hollow-worn wheels, which is now the damage phenomena here, if you've got a lot of hollow-worn wheels, your rolling resistance of that wheel will be higher. So if you've got a number of them, the rolling resistance of the train will be higher, and thus your fuel consumption will go up. Hollow-worn wheels have got also the tendency to make a stable vehicle unstable again, which will induce new forces into the system, new wear mechanisms, and even ultimately new safety threats. Alternating rail gauge face wear, I will come back to that example a bit later in more detail. The wheel tread wear itself, if the flange effectively after a lot of wear seems to be higher than it originally was, it could contact some of the track components and cause damage to both the wheel and the rail, or even a derailment. The next damage phenomena is polygonal wheels, meaning that there are polygons or waves around the circumference of the wheel. In this instance, for example, it's 20 of those little waves around the circumference of the wheel. What this can cause is impact damage, let's say to the track structure or to the bearings and so on. And on top of that, it could also cause vibration damage, because if you roll this wheel now at a reasonable speed, you're sitting at 40 km an hour more or less with 70 hertz frequency. So it starts vibrating the bogie components. So we as vehicle dynamics specialists, we usually stop doing our models and we say, if you're above 10 hertz, we're not interested in that anymore. But as soon as you introduce these kind of problems in your modeling, in terms of your analysis, in terms of your experiment, all of a sudden you have to do vehicle dynamics analysis, not only up to 10 hertz, but you might have to go to 200 hertz to be able to show that you capture all the important frequencies, that you can understand the long-term behavior, and then do the corrective actions. The other damage phenomena is grooved wheel tread. Generally, when the brake block is of an inferior quality, or it has disappeared and you have got the brake shoe rubbing directly on the wheel. So it's a very operational related issue, but it causes this wear phenomena. Turning our attention to the rail, we've got rail side gauge wear, and that will give us a shorter rail life because we cannot restore this profile sufficiently for a long period of time. Then we've got the opposite of the polygonization. We've got the same phenomena in a way on the rail corrugations. Also, it can be a wear phenomena. It can also be a stress phenomena. Quite a complex area to understand and to decide what's wrong, because it is sometimes a fatigue problem. It depends on the load. It depends on the curvature. But it is one of the examples of long-term behavior. Then alternating gauge phase wear is a phenomena which one sees in various places in the world. We have got a particular challenge which we have to look after on a regular basis, and that is this kind of phenomena on our iron ore line. Our iron ore line is pretty straight, for argument's sake. The vehicles are uniform, all of them are the same, and they are short wagons because iron ore is heavy, you don't need a big wagon. And these kind of wagons then have the tendency to go from left to right once disturbed by a bad rail joint or by a level crossing, and they cause then side wear in the rail here. Then it will jump to the other side, it will come back, so here's one wavelength of alternating side wear. And in these areas we will then have rail side wear again, gauge phase wear, and that will shorten our life. And the problem is, if this starts occurring, it can grow very quickly because it lives on itself. The more you roll over it, the more wear there is, the more of input it gives to the vehicle. So it's very important to control this, and the way to control that is to control your rail profile and control your wheel profile. Okay, so I think we've discussed the alternating gauge phase wear, and that leads then to shorter rail life. Okay, another wear-related phenomena which we quite often forget that it is wear-related is noise. It can be flanging noise, rolling noise, squeal, wheel squeal, curve squeal, screeching noise. It can also be the noise through impacts. So what we see here on this slide is the experiment which we set up on our iron ore line in a 1,000-meter curve. And we've got those microphones positioned exact distance from the rail and exact heights according to specification. And then we have started, and this project goes for a number of years already, measuring passing trains. So what you see on this very busy graph there in the center part, you can see most of it, is now the noise generated by the passing train in terms of the frequency over distance. So what we're seeing at this stage, this is the one set of locomotives. Here's the second one, third. There's actually a fourth one. This is our 346 wagon train, which we run a few of each day of the year. And what we see here is these sort of vertical lines. They're basically saying that the noise generated is tonal. It's like a piano. You can go sort of in steps and you can have your music sorted out. So this indicates that it is wheel and squeal. Another graph would have more of the vertical kind of behavior. Then we talk about flanging, for example. So by just studying the noise level, we can also determine where it's coming from. How to solve it is a bit more difficult, but the most important thing to remember now is that it is also a wear-related phenomena which we can control. Stress-related damage, the rolling contact fatigue, which we're getting between the wheel and the rail, mainly on the gauge corner and even on the field side. So what we've got here is a wheel that has worn very hollow here next to the flange. Flange wear is included. Then there is we call it a false flange. It's a bit of a similar thing, but it's on the field side, which causes a small area of contact, and the consequence is this kind of fatigue damage on the field side of the low leg. On the high leg, we've got that bump of the wheel which has not worn away because the wheel was running there. We cause head shaking and the gauge corner of our rail. So these are long-term stress-related damage which we have to control, and this is where, for example, the wheel and the rail profile criticality comes in to do that correctly. Further examples of stress-related damage. Here we've got another picture of rolling on fatigue. Don't rub your finger in that direction. Don't. Then we have got subsurface initiated shelling here on the second picture, and then surface initiated spalling. So the damage both on the wheel and the rail, they Isaac Newton's second law, action reaction. The one is subsurface, so it depends on the cleanliness of the material, whether there are any subsurface hidden defects. That would then initiate a subsurface defect, where the rail surface or the surface defects really start on top. The top material is deformed and then slowly a crack is formed and it grows into the rail. There's other things, squats over here, and then if you've got rolling contact fatigue and you leave it too long and you don't know what's going on in your rail because your ultrasonic measuring car can't see there because it has got too many of these rolling contact fatigue cracks, then we could have a fatal rail failure, a rail break, and quite often that goes then together with a derailment. Another stress-related issue is a metal flow. Here we typically get spread wheel rims, gauge corner collapse here on the second picture, and sharp flange tip. So not only is the flange worn thin, but on the tip of the flange there is metal flow, and if this wheel, which is now thin and has got the metal flow, approaches a turnout with the points not set perfectly, it will find its own way between the points plate and the stock rail and derail, or it could climb up onto the points plate and derail in that way. Stress-related dipped rail joints, joining rails to have continually welded rail is an art by itself. Various techniques are used, but the problem is if the technique causes, here is the weld itself, then there's the heat effective zones, and you get a difference in the material hardness, and if you've got a difference in material hardness, you will get metal flow, and you will get a bit of a dip on the rail, and the train will pass, and another train will pass, and eventually where all of these rails are, we have got deteriorated ballast, because now we're putting the impact into the track structure and it is damaging our ballast, and the next train enjoys it even more, and then you got problems. Now you have to replace your ballast, you have to fix your geometry at the weld through grinding. Operational related damage. Here we've got, for example, thermal cracks. If we've got the brake block and we've put it on too long and too hard, the material will heat up and cause thermal initiated cracks. Skidded wheels, or wheel flats called. So here we've got a smaller one, here we've got a bit of a bigger one. Sometimes it's due to cracking, sometimes it's purely due to sliding, but whatever it is, it will cause a high impact load into the track structure. Spin marks on a rail crown, that's opposite to the skid marks on the wheel, also causing the high impact loads to the passing vehicle and also simultaneously down into the track structure. Metal built up due to the incorrect choice of your brake block, due to some material problems on the wheel, will also cause impact loads to increase and cause damage to the brake block. And although this happens pretty quickly, it's one of the long-term deterioration behaviors of our system. The dynamic related damage, here we're looking at vehicle hunting. If the vehicle has got severe hunting properties, it will cause rolling conduct fatigue damage because the forces have increased. It will cause increased wear of the wheel and the rail. The track structure will be deteriorating because the rolling stock is now really putting a lot of forces, high loads into the track structure. And if we don't stop at that stage, we might even derail the vehicle. Vehicle track interaction specifically, we can cause an accelerated rate of the component deterioration on wear of both the rolling stock and the track structure. It gives us a shortened fatigue life for our whole system and can also cause derailments. So what do? We have to monitor all of these phenomena and interpret what we're seeing. We can do this by direct measurement of the track geometry, or by indirect, by measuring, for example, forces or accelerations. So one, we know exactly after measuring it, we have got now the rail geometry or the wheel geometry. The other one, we have got a force, and we need to compare that to what is an acceptable force, and it's not. So we have to make sure that the limits must consider the life cycle costs. We cannot just do our engineering part. We need to look at life cycle costs. We need to look at reliability. Is whatever we're going to do be reliable? Availability in terms of the maintenance cycles, are we going to affect that? If we put a limit force on which is too stringent, our maintainability and availability will be influenced. So we need to be realistic about our choices of limits. And ultimately, we need to make sure the system is and stays safe. So this brings us to the idea of using preventative and corrective measures. That would be looking at an alternative bogie design. And a bogie design needs to have good wheel load equalization, which means if this bogie runs over track twist, all four wheels must have a more or less equal loading nevertheless. So we need to have a suspension system which is flexible enough, which is able to allow that we retain a lot of load on the rail, and in doing that we will not cause unnecessary track damage. We need to make sure that the bogie design has maybe improved hunting stability or improved curving performance. Now, unfortunately, hunting and curving, they are not on the same page in the book. If you do good for the one, you lose on the other one generally. But quite often we just need to know, under which speed we need to be stable still, and then optimize our curving behavior for that particular bogie design. What's very important also in terms of doing preventative or corrective work is to do bogie condition or track condition based maintenance. We also have to look at the brake system, and the brake system itself, the design thereof, the rigging design, is it going to last? Is it going to work efficiently and is not going to get stuck halfway down the road? The brake shoe coefficient of friction, that will influence not only stopping speed, but also stopping distance, but also the influence on the heat that goes into the wheel. And the last one, as I said, the heat input into the wheel. So we cannot stop our trains at 50% shorter than we currently do, because then the heat input into the rail, into the wheel, will cause unnecessary fatigue damage or heat-initiated damage. The wheel and the rail profiles, again, are very critical in minimizing the costs of doing a railway business. And we have to be very conscious of using safe and economic-based criteria to remove or to reprofile our wheels and rails, because those are the most costly elements, as you will see in a moment, of our railway system, the wheels and the rails. And they are the ones that we have to look after to get the win-win situation. Furthermore, there's other strategies which one can follow. The one is lubrication and friction management. Here we look at lubricating the gauge face of the rail or the wheel flange. We're looking at consequential savings in wear and energy costs, because now the wheel is easier to go, it's easier for the wheel to go over the track, less resistance, less wear. Then also, which is applied selectively all over the world already, is top of rail friction management. It's where we don't call it lubrication, because we're just bringing the coefficient of friction a bit down to a more manageable point, and that's where we manage that, and that's where we get the most benefit, because the benefits are related to reduced lateral curving forces, and I've seen it myself in on-track tests. The locomotive went through a curve without any lubrication, enormous forces. Putting top of rail on, was not sure whether the loco had passed. The forces changed significantly. Then also associated with preventative and corrective maintenance and measures is the rail grinding strategy of your railroad. Shaping the transverse rail profile. So we need to keep our rail profile close to the design profile. So that is where grinding can help us a lot. And then also to control simultaneously the rolling conduit fatigue. Now, unfortunately, sometimes the rail wears where you don't want to reprofile it because it will change your target profile. This is where you have to put more grinding stones on and grind, make more or less what we call a full cover grinding. So back to the stress state. What we're seeing here is the, for general freight business, we're seeing a very wide distribution, both on the traffic coming in, meaning the loads and the forces, and a wide distribution of the track strength parameters. And for that we do get then an overlap as indicated there. What we're seeing next to that on the right-hand side is a similar situation as we shown earlier in the presentation, the heavy haul traffic forces and the heavy haul track strength. And we can see it shifted a quantum towards your right-hand side. But both of them, the general freight business and the heavy haul traffic, shows that the worst wagon meets the weakest track, and we need to look at that. The only forgiving thing is that for the general freight business, we are at a more forgiving place. We have got less traffic potentially, but definitely lower forces. So we would apply our strategy slightly different. If we come to the heavy haul, we know it all. We've got extremely high forces, and people keep pushing, and by doing that, they keeping Steve and Marich busy. So the track engineer has got rail problems. So what he does, he goes and buys stronger, harder rail. So here we got the strong and harder rail. I'm scared to push this thing. This one should actually be an animation, but we'll talk through it rather. And then some stage later, the rolling stock guys say, oh no, sorry, we've got the track engineer who's identified rail problems. He does buy a couple of new rails, puts them into service, and there comes an instruction, we're going to go heavier, which means the rolling stock will now be heavier, there will be higher forces, and that will move this histogram over to that area again. So what is basically happening is a game between the rolling stock and the track, because the rolling stock guy has now seen his wheels are wearing, his wheels have got rolling corner fatigue, so he does his own thing. So the important part is there must be a multidisciplinary approach applied. So we need to have better materials and better design. So we move everything to the one side, but we have constantly, we are filling this gap, which is not what we really want. If we do better maintenance, we can pull in the distribution and have the whole system more manageable. But all in all, coming back to the beginning of the lecture, is we have to have a balance between the operational demands and the essential maintenance interventions and the related costs. So this is quite a tricky balance. So we need to have information once we've got the understanding of how the system works. So many system components, unfortunately, as I mentioned in the beginning, deteriorate exponentially with increasing wheel load. So the damage goes up exponentially. So for such a system, it would be cost effective to conduct maintenance more frequently, so that we can catch it here before it runs away with us. So time-use track tamping, rail grinding, bogie maintenance, and wheel profiling is very important. But we need to know which one first and which one is second and third in the row, depending on our budget constraints. So for this, I used a formula and work developed in Canada a while ago, quite a few years ago, but they defined a wheel load damage factor, which is really a function of the increased wheel load with respect to a reference wheel load and the damage that could be caused by the components when they interact. So we've got increased wheel load over the reference. So maybe we want to increase axle load from, say, 30 ton to 35 ton. So we would be having 35 over 30, and then we will have an experimentally determined damage factor which we can plug in there, and we can see what the effective damage factor would be of one part of your system against another one. So here is an example of some track components. What we can see on this table is that 70% of the total maintenance cost is related to rail. That's now in the infrastructure, 70%. We see 10% on sleepers, and we see 20% on ballast. Now what we do see when we look at this graph, if we have got if we have got good track, the damage factor is 1, okay? Which means there's a linear relationship, and it's well and easy to control it if your track is in a good condition, the track geometry and so on. But if it's in a poor condition, look at that influence on your maintenance. It shoots right through the roof, and causes unnecessary expenditure on trying to control that. The problem is once you have gone over a certain limit, you almost have to replace everything. So we need to understand the difference in terms of the influence of these parameters. If we look at surface fatigue against internal fatigue, we can see that both have got a similar fatigue factor and damage factor, but probably by rail grinding we can address both. So these are the kind of considerations you need to make before you start spending the money. But the considerations are also linked to in-depth understanding of the wheel rail and the vehicle track interface. Here is a similar table for wagon components. On wagons, also 58% of the costs go into the wheels and axles. So again, that's why there is such a lot of focus on these. That's why we are having wheel rail interaction workshops and so on. So on this one, 50%, sorry, where are we now? Okay, so it's 58% and 50% is due to wear. But the damage factor is only 1. So that's okay. But if we look at the journal fatigue, it's only 1% of the problem, but with a damage exponent of 9. So don't leave that alone. If it's time to replace it. So in that way you will make your decisions and you will be able to achieve a better operational efficiency. So the focus really is on the critical items. So to end my lecture here this evening I just want to state what Professor Roderick Smith from the London Imperial College was saying. In the vehicle track system, which is married at the wheel rail interface, anything less than a good condition of both the vehicle and the track causes a vicious spiral downwards to a bad condition of both. I thank you for your attention.